Alright, so this is going to be a lesson on 4.2. Now, the do now question says the blue vector represents the horizontal velocity, and the red vector represents the vertical velocity. The question then goes on to say, well, does my horizontal velocity change as the projectile is launched through the air? And what about your vertical velocity? So you see in this GIF, right, you see in the top right-hand corner, you'll see that your horizontal velocity stays the same, whereas your vertical velocity changes as time goes on. And why is that, right? Why does the GIF show that my vertical changes, but my horizontal velocity is constant? And the reason here is that, well, due to the acceleration due to gravity. The acceleration due to gravity only acts in the y direction. Right? My acceleration due to gravity only pulls me downward. It doesn't really pull me to the left or to the right. My acceleration due to gravity only acts down in the y direction. And again, your acceleration is your change in velocity over time. If you have a velocity, you have an acceleration. Therefore, the acceleration due to gravity only acts in the y direction here. And in the x direction, my velocity is constant. There is no acceleration. So we get to this slide, right? So the unit we are on is called projectile motion. Projectile has a very specific meaning behind it, right? A projectile is essentially anything that only has a force due to gravity acting on it. And the projectile is, so for example, if I'm holding an object, right, in my hand, I'm exerting a force upward from my hand, right? And so that's an applied force, which means that the force due to gravity is not the only force acting on it, which means the object is not a projectile. If I were to say, if I kind of throw the object up, well, now the object will be a projectile because there's only the force due to gravity acting on it. And that's going to be your projectile, right? It's going to be called projectile. But once the object lands back into my hand, the object is no longer a projectile. The object is just an object, or whatever it's called. So that's the situation an object can be classified as a projectile. Now, the mere act of throwing something up, right? So the mere act of throwing something up. So let's say we launch a ball upward. Launch a ball upward. So we start here, right? And we throw it upward, and then it comes back down. There are certain assumptions we can make about an object in that motion, right? There are certain assumptions we can make here. And this diagram on the right kind of shows the position of the ball each second, right? So it's at 1, 2, and 3 seconds there, and then at 4 seconds, oh, 4 seconds. My 4 seconds is there, then 5 seconds, then 6 seconds, all the way back down. Yeah, right, and there are certain assumptions we can make here. And so the first step assumption, and you see on the right-hand side, right, the first dot, the first dash says, what is something you can assume about your vertical velocity at its highest point in its path? At the highest point in its path, my vertical velocity will be 0. At the highest point in its path, my vertical velocity is 0. Think about it this way. You throw an object up, right? An object up, it kind of gets slower as time goes by because you see the distance increases, right? You see the distance between each second increases. And you get to a point at the top where your object stops briefly, momentarily for a split second, right? It's barely a moment in time. And at that moment, at its highest point in time, my velocity is 0. But then right after that, right immediately afterwards, the ball starts going back in the opposite direction. And then the ball starts speeding up in the opposite direction. But the takeaway here is that, well, at my max height, the ball briefly stops for like a split second, and its velocity at its highest point is then 0. You can assume it's 0 at its highest point. Now let's move on to the second dash, right? So it says time up to its highest point, time back to its launch height, right? So what are some assumptions we can make there? don't know why I have this here. Okay. Some assumptions we can make here is that, well, you can look at it, right? It takes 3 seconds to go up to its max height, but then it takes another 3 seconds to come back down because you see the time of 6 seconds. Right? So it takes 3 seconds to go up, 3 seconds to go back down. So you can say that, well, my time upward, is the same time it takes for the object to go back down. So same time up and same time back down. Right, so my velocity here will be 0, right? And I'm just going to fill that in retroactively. And now let's go to the third dash point, right? What can we assume about my vertical distance up and then my vertical distance back down? Well, we can essentially assume that, well, if you travel, I don't know, let's say 50 meters upward, well, then I travel another 50 meters downward, right? And so that my displacement would be negative 50 meters. And so we can say that, well, they are the same, right? So we can say, well, my distance up is the same as my distance down. What about my vertical displacement? Once it goes back to its launch height, right? We launch at a certain height and then it lands back at the same height. What can we say about my vertical displacement? Well, my vertical displacement here would be 0. I didn't move anywhere, right? My displacement again is, well, how far are you from where you started? Well, if you land at the same spot, if you land at the same height, you are 0 meters from where you started. So you can say here, well, that my displacement in the y direction is 0. Let's look at the last assumption we can make. Well, what can we assume about the signs and the magnitudes of your vertical velocity up and down? Let's take a look at our initial velocity. Our initial velocity is positive 29.4 meters per second. And when the ball lands back down, you can see that, well, my velocity there is negative 29.4 meters per second. So what can we assume about the signs and the magnitudes of my vertical velocity up and down? Well, we can say that, well, they have the opposite signs, right? Clearly, because if you're going up, you have positive velocity, and if you're going down, you have negative velocity. So they have the opposite signs, but they have the same magnitudes, right? Their numbers are the same, right? They have the same size. They're both 29.4 meters per second, but the only difference here is that they're acting in different directions. One is going up, the other is going downward. So those are kind of all the assumptions you can make regarding symmetry of freefall. Right, those are assumptions you can make. And then this is kind of just more review, right? So your hang time is essentially the time it takes for the object to land back at the same height. So for example, if it took you 4 seconds to go up to your max height, well, it's going to take you 4 seconds to come back down, which means that your total time that you spend in the air is 8 seconds. If, for example, I take 8 seconds to go up to my max height, well, the total time my object spends in the air is 16 seconds, right? Because it's 2 times your time up to max height. And let me give you another example. If your total time in the air was 20 seconds, well, your time spent going up to your max height would be 10 seconds, right? It would be half of that. And these are assumptions you kind of have to make here. And we go back to our symmetry of freefall. Think about it, right? Symmetry is essentially the same thing on both sides, right? Both sides are symmetrical, both sides are the same. So when we're solving problems, we can either analyze my side up, right? We can either analyze my path upward, or I can analyze my path downward instead. Because again, everything will be the same on both sides, is that, well, they're opposite directions. And this will be clear, much clearer when we go over practice problem 2E, right? But before we get there, let's do a few practice problems, right? There's a few practice problems in front of us. So, a ball thrown vertically upward reaches a max height of 30 meters above the surface of Earth. And so you can say, well, my dy here is 30 meters. At its maximum height, well, what is the speed of the ball at its maximum height? Well, this is an assumption you can make, right? At your max height, you can assume that, well, my velocity in the y direction is 0 at my max height. At my max height. All right, it's an assumption you can make, right? It has to be. It has to be. So let's take a look at this question right here. A ball is projected vertically upward from the surface of the Earth with an initial speed of that. So my initial velocity in the y direction, right, you're projecting it vertically upward, is 49 meters per second. The ball reaches its max height in 5 seconds. Right, so my max height, reached my max height in 5 seconds, right? So you're going to go upward, and the question says, well, what is the max height reached by the ball? So what is dy? There are two assumptions you can make here, right? You can make the assumption, well, at my max height, my velocity, my final velocity, right, because we're analyzing our path upward, my final velocity is 0. And we can also make the assumption here that, well, this object is clearly on Earth, which means that, well, you can say that my acceleration due to gravity acting in the y direction is negative 9.8 meters per second squared. Now we have 4 knowns here, which means we can use 2 formulas to solve for dy. It doesn't really matter which one to use. But we're just going to make it easier for ourselves, and we're going to say that dy is equal to, we're going to use this formula, right? It's on your reference table. And again, the y's I'm adding is because it's just saying that this is your vector acting in the y direction. Right, you guys are used to this formula here from your kinematic formulas, right? So that's that. So dy, d is equal to vi, which is 49, t is 5, a is negative 9.8, t squared is 5 squared. 49 times 5 gives you 245. 1/2 times negative 9.8 gives you negative 4.9. 5 squared gives you 25. 245, and then negative 4.9 times 25, I get 122.5. And then doing the math here, you get this, right? So your max height that this object reached is 122.5 meters. So what's the velocity of the ball as it returns to the point from which it was thrown? You're continuing the previous question. Again, the previous question said that, well, the initial velocity in the y direction was positive 49 meters per second. And the question, well, is asking, well, once it goes back to where it started, right, the same height, well, what's my velocity? Again, this is a symmetry of free fall assumption. You know that, well, my velocity is the same, well, it's just acting in the opposite direction, which is negative 49 meters per second. Right, so it's pretty much the same, just opposite side. That's the velocity of the object once it goes back to where it started. 2D, what is my total displacement of the ball from the time it is thrown until it returns from which it was thrown? Right, so what is my displacement? Right, the ball goes up and the ball lands back at the same height. Well, if it lands back at the same height, right, your height is 0, and then you land at a height of 0, well, my displacement in the y direction will be 0, right? Displacement in the y direction will be 0. Because the displacement, again, is essentially how far are you from where you started, your final position minus your initial position. That's displacement. So your displacement, you land back at the same spot, your displacement is 0. Let's get to this 2e. So a basketball player jumps straight up, right? Jumps straight up to grab a rebound. And then if she was in the air for 0.8 seconds, right? How high did she jump? Now, here's the thing, right? You're looking for how high she jumps. So essentially, you're looking for her either her path upward or her path downward. So you're looking for half of it, right? So dy is what? You're looking for half of her path. And if you're looking for half of her path here, well, if the total time she spends in the air is 0.8 seconds, which means that if she not only goes up and comes back down, and that entire time there's 0.8 seconds, that means that her time up to her max height, here is half of her total time. Her time up to her max height is 0.4 seconds. And what is my, and there are certain things we can assume here, right? We can assume that, well, if the object is in the air, the object is a projectile, our acceleration in the y direction is negative 9.8 meters per second squared. And not only that, my velocity, my final y velocity is 0. My final y velocity is 0 there, because again, we're looking for at our max height, right? My velocity at the highest height is 0. But here's the problem, right? Here's the perplexing thing is if you try and look at your kinematic formulas, if you try to look at any kinematic formulas, you'll realize that, well, you can't really use any of them, right? And the closest one that most students think is that, well, why can't I just use this one? Right? Why can't I just use d is equal to vit plus 1/2 at squared? Right? Why can't I just use this? And the reason being is because, well, you don't know your initial velocity. You know your final velocity, but you don't know your initial. But here's the thing. The idea of symmetry. We can either solve for our path upward, or we can solve for our path downward instead. Because we know my distance up is the same as my distance coming back down, just the opposite sign. And instead of saying that my final velocity is 0, instead of saying I end at my max height, let's say we start at my max height and we end at the bottom. So we can say that, well, my initial velocity in the y direction is going to be 0. So now can we use the formula? Now can we use the formula here? Yes, we can, because now we have our initial velocity. Right, so now dy is 0, and then 0 times anything is 0. Right, 0 times t would give you 0. I'm just going to write that entire thing as 0. This, and then you have 0.4 squared. So dy negative 4.9, 0.16, right? 0.4 squared is 0.16. And then you get I think you get this. I think you do. Let me just calculate real quick. I'm just trying to recall from class. You actually get no. Okay. Yeah, you get this. So you get a negative number here, right? You have to carry down a negative because there's a negative sign there. But that's not really your answer, because that's your path downward, right? Your displacement. Your height, how high did she jump? You can't really have a negative height. So she jumped 0.784 meters, right? So she jumped 0.784 meters. And that's the answer, right? That's the answer. So to F, a soccer ball kicked on a level field has an initial vertical component. So my initial vertical component is 15 meters per second. Assuming the ball lands at the same height, lands at exactly the same height from which it was kicked, right? So if you kick a soccer ball, the path the soccer ball will make is something like that. It lands at the same height. What is the total time the ball is in the air? So you're looking for total time. And there are certain assumptions you can make here, right? You can make the assumption that, well, my acceleration in the y direction is negative 9.8 meters per second squared. And we can also make the assumption here as well that, well, my velocity at my maximum heights, my final velocity, because let's just say it is 0. And we can solve for our equation like this, right? We can say that, well, VF, V final is that, and V final is 0, VI is 15, negative 9.8 T, 15, negative 9.8 T. Then you subtract that on both sides. Divide that. And then I get a time of 1.53 seconds is T. Okay? 1.53 seconds is T. That's the answer there. Oh, no, I'm sorry. That's not the answer. It's saying that your time up to its max height is 1.53 seconds. Sure, my time up to my max height is 1.53 seconds. But the question is asking for your total time. The total time the ball was in the air. And you have to realize that, well, if my time up to my max height is 1.53 seconds, it's going to take another 1.53 seconds to come back down. So you actually have to multiply this number by 2. So my actual answer, right, my total time is 3.06 seconds. Right, that's my total time. All right. Okay. There's actually another way to solve for this. Right? There's actually another way. Let's actually erase all of this. Well, I can't, because that's not really, well, I can do it like this. Let's do this. Let's erase this too. So the other way, without having to take multiple steps, is you have to realize that, well, you land at the same height. And if you land at the same height, well, you can say that, well, dy here is 0. My vertical displacement is 0. I land at the same height. And then the formula we would use to solve for this equation is this one, right? So d would be 0, vi would be 15, t, 1/2, negative 9.8, right? So t squared. And then let's just solve everything, right? So minus 4.9 t squared, minus 15t on both sides. So now negative 15t. And then what you can do here is you can divide by 4.9t, cancel out the t, right? And then we get, I mean, you should get 3.06 seconds. That's what you should get, right? So actually, no. There's no square here. The square cancels out, right? Because the t squared and the t is going to give you t, right? So 3.06 seconds, and that would be your answer. So that's how you would solve it the second way, right? So you can solve it the second way. All right, that's that. That's the